Alright, welcome back to the classroom. I'm Mr. Wong, and today we're going to be covering Module 3, Waves and Thermodynamics, Inquiry Question 3, Sound Waves, and the dot point of focus is this: investigate and model the behavior of standing waves on strings and pipes. Look at things such as fundamental and harmonic frequencies, producing based on characteristics of length, mass, tension, wave, velocity of the medium. So, like we said before in the previous lesson, waves can be broken into two types: mechanical and electromagnetic. Sound and light are just some examples of each of them, but at the end of the day, even if they propagate in a different way, they still represent the same type of behavior. So our investigation today is firstly look at certain features of standing waves, and then try and implement this understanding in how to we produce music in string instruments. The next lesson we're going to look at pipe instruments as well. Okay, so let's just start off. So the difference, have a look at these two waves that we have. Previously we talked about a concept called superposition, the concept where you have two waves that kind of interfere with each other. Depending on how they interfere, as you can see with this dark line here, it could be at 0, it could be at its maximum displacement, so double the length in the vertical direction. Now, progressive waves are waves that appear to be moving. So you could think of progressive waves as waves from the water. Okay, so you have the water moving the wave along. That's a progressive wave. The next type of wave we have is a standing wave. Now this occurs because of some kind of interference between two or more waves together. And what that actually does is it gives us a nice little pattern of music or sound depending on what tones we generate. Okay? But what we will see is when we create standing waves, there is an increase in amplitude of the two waves added together, and it doesn't look like it's moving. It just looks like, if we look at this standing wave that we have here, you can see overall it's just propagating between 2 points. The wave itself, this bit, this bit, this bit here, they haven't actually moved at all. So that's what we mean by a standing wave. So we're going to look at how that relates to musical instruments. Okay, let's try and form a standing wave. So superposition comes from the combining of one incident ray and one reflected ray. They could be moving in opposite directions to each other, could be same directions, but we're going to try and show that very shortly. Okay, so you can see our little standing wave here. If you actually have a look at this side of the wave, you can see the wave is just sort of oscillating up and down. What's actually happening is we're getting a pulse generated from this little oscillator moving over here, and this little ring is loose, so it kind of moves up and down for us. That also reflects the waves back, so we get two waves being reflected backwards, and that actually helps demonstrate sort of a standing wave structure here. So it's just moving up and down. It doesn't appear like it's moving at all. So that's sort of an example of the standing wave. If we actually look at some features of standing waves, you can find a couple of things. In terms of formation, you need at least two or more waves of similar frequencies and amplitudes trying to interfere with each other. When that happens, you will generate a node and you'll generate an antinode. Now, what I said before from the previous lesson, node, when you get the node, that means there's zero displacement, and if you see that in the standing wave, that's where you get a complete destructive interference. So the waves, the maximum of one wave is or interacting with the minimum or the opposite maxima of the other wave. The antinode is where we get constructive interference, so they combine to make a bigger wave, and that's where we get maximum amplitude. if you were to calculate the antinode, so from one antinode to another antinode, the overall distance, let's say it's whatever x meters, times that by 2, and if you know the frequency of the source, you can actually work out the wavelength. So let me just kind of point that out again, because I'm going to show a little demo here. I'm not going to do any calculations. So if I know the length of an antinode or any node, so let's say the length of a node to another node is half a wavelength. So 2 times the length of a node and antinode, or you could say after counting 3 nodes, is 1 whole wavelength there. So that's what we got. What I was saying before is if I know the frequency of the source that I'm generating, and I also know the wavelength, I can work out the speed of that wave. Okay? So I'm going to show you a nice little thing here. We're going to use a signal generator of 340 Hertz. So I might need to change up the setting a little bit. And the predicted wavelength is 1 meter. Okay? So the velocity of that wavelength times frequency times wavelength, 340 times 1 meter, it means that the wave that we're looking at should be traveling at about 100 or 340 meters per second. Okay, what I'm going to try and do here is I'm going to actually turn the speakers on for my laptop, and I'm going to be moving the microphone in my headset to give you that sort of difference in tones as I move through, and you can actually hear where we have the antinode. So where you hear maximum volume, that is the antinode location, and where you hear the node, that's where you should hear a minimum amount of volume there. So instead of using 340, I'm going to use 440 just because that's the original setting, and then we'll go with that. Okay, so we have a signal generator of 440 Hertz. I'm going to put my headset directly next to the speakers of my laptop, and that, at least when I was trying this out, was the maximum volume I heard. And I'm going to progressively move my head away, and you should hear that subtle drop in volume of the signal. So you can hear the sound. I'm going to progressively move my head away. And you can hear the sound slowly progresses. If I move in opposite directions, you can hear the signal kind of build up. And if I move my head back closer, it gets louder again. Awesome stuff. So that's just kind of showing you the node antinode of how sound works. So let's actually get into how to work out the pitches of sound we have. Now, in order to calculate the wavelength of any wave, best way to work on it, you can base it on the crest or the troughs. Another way is you can use the nodes and antinodes. So if you find a wave like this one we have here, change it to my highlighter, laser pointer. If you just have these two, that's a quarter of a wavelength. If you have a formation of half a wavelength, you should be able to count 2 nodes and 1 antinode. So this is a half a wavelength. The formation of 1 wavelength would have 3 nodes and 2 antinodes. So that is what a wavelength is. So if you're able to do that counting point there, then that's a wavelength that you're dealing with there. Okay, so keep that in mind. Okay, from before, we talked about the concept of frequency. So we said that things will naturally vibrate at a particular frequency here. We call that the natural frequency or the resonant frequency. If we are able to then imply some kind of shaking motion to it, the motion of this man here moving these circular spheres, that's a driving frequency. So you're putting in vibrations causing the object to vibrate. Under the circumstance where the driving frequency and the natural frequency match each other, so we say the natural and the driving are of the similar frequency, then you get a thing called resonance. Resonance, basically what we're talking about with superposition, we get a higher volume, greater standing wave, and such. Okay, now we're going to talk about physics and music. Now this might seem a bit odd for some of you, but the tones we generate, the different harmonics, the different overtones we generate in music is actually governed by some very simple scientific theories of physics. So the thing we want to note is each pitch or each tone we generate in a musical instrument, each tone is a specific integer. Integer is basically a whole number ratio. So every tone we generate, let's say on a piano, let's say on a violin, it has a specific integer that matches up with that particular tone. Each successive tone we generate, obviously we're increasing the amount of integers we have. Okay? Obviously, if we're increasing the tone, we're increasing the integers, thereby meaning we're making the wavelength smaller, then obviously we get a higher pitch. Okay? Which kind of shows here in this diagram what we call the fundamental, so the most basic frequency that can't go lower. That's usually the lowest pitch tone you can generate, and as you generate more wavelengths, shorter wavelengths, you'll get a higher pitch overall. Okay, so what we're going to focus on in this lesson is string instruments, which we're going to say is two closed ends. And then in our next lesson, we're going to look at wind instruments, which are instruments that have a fixed end and a closed end. Okay, so that's what we're dealing with here today. Okay, so let's just start ourselves off. There's a couple of wordings here that you might not be familiar with. We have the fundamental tone, or the first harmonic, the overtone, harmonic, and all that. I'm going to go through a bit, and we're going to also look at how we generate these kind of equations. Okay, the first thing you need to note in musical instruments is the concept of harmonics. Harmonics just means vibrations. If I generate a harmonic, I'm generating a vibration. That's how sound works, right? If you're making sound, you're trying to make the air around you vibrate to translate or transfer that specific energy across to a listener. The lowest possible vibration you can generate, sometimes we call it the resonant tone, we also call it the fundamental frequency or the first harmonic. Okay? If you make other vibrations of a higher pitch, what we call successive harmonics, higher frequencies, we start calling them overtones. So the very first pitch of sound you make, the lowest one possible, that's called the first harmonic or the fundamental frequency. If we go a higher pitch, that's going to be called the first overtone or the second harmonic. Sometimes people might designate it as N2 to represent it's the second harmonic. You could do that as well. So second harmonic or first harmonic can be N1, second harmonic can be N2. Okay? You can use this little simulation to sort of work out the trend. So we're going to actually use this simulation to work out some of the trends of these types of instruments. The ones we're focusing on is 2 fixed end. So the link will be down below on this video. You have 2 fixed ends of instrument in an instrument. So that could be a violin, any type of string instrument. We're going to find that the length of the string will dictate to us, depending on the harmonic we make or the vibration we generate, how many wavelengths we'll see on that piece of string. Okay, so a little blooper already here, but let's just start with the first harmonic. So for 2 fixed or 2 open end instrument, I get this particular wavelength here. Now what we said before, if we have 2 nodes and an antinode, that's half a wavelength. So for the very first harmonic for 2 open ends, we get half a wavelength of this particular sound wave. In the second harmonic, or our first overtone, we have generated a singular wavelength here. So n, if you recall, in our general formula, the length of the string is the number of harmonics we see divided by 2 over lambda. Okay, or at least this is just showing us which harmonic we're in. So we're in the second harmonic here, okay, and we find that we generate 1 wavelength. Okay, that's pretty straightforward here. When we go to our third harmonic, we find that we have generated 1 wavelength and a half. Okay, so 3 over 2 wavelengths here. You can see, this is the way I'll count it up. We have 1, 2, 3, 4. So 4 nodes. 1, 2, 3 antinodes. Okay? So if this is 1 wavelength here, this is an extra half, as you can see with the 2 diagrams we've shown above. So 3 over 2 wavelengths. We can actually show a general formula for this. We can actually say that the length of a string on a 2 fixed end instrument, it will be n divided by 2 wavelengths. Same what thing, we can rearrange the equation and find that the wavelength of 2 fixed end musical instrument will have a length of 2L divided by n. And that's also our way of working out the wavelength. The other one is our way of working out the length of string we need to generate that specific harmonic. If the string isn't long enough, remember this is an integer, so we can't have numbers in between. If we don't get the exact number, then we don't get the specific tone. Let's look at if it was 1 fixed end and 1 open end. Okay, if it's 1 fixed end, we get half a wavelength, or a quarter of a wavelength, sorry. The way we work this out is we only have 1 node and 1 antinode. This is what I said before in a previous 2 slides. Okay, that's a quarter of a wavelength there. The next one we have is 3/4 of a wavelength. You can see we have our 2 antinodes, but we only have 2 nodes here. Okay, we're still missing another sort of node coming across in that direction there. So that's 3/4. The last one we have here, you can see that's a full wavelength here, and then we have another quarter of a wavelength. So 4 over 3, or 5 over 4, sorry, wavelength seen there. So the general formula we can write here if you actually have a look, is 2n minus 1 divided by 4 lambda. So that's the general form that we have here. Now, why do we call it? Now, what you might also notice is I've been calling this the first harmonic and then the second and the third. Well, actually, we do change the names up. We call it the third harmonic and the fifth harmonic. Now, the reason being, in the first harmonic, when n is equal to 1, let's sub it into the equation. 4, that's 1 over 4. Okay, in our next one, in the second, or in the first overtone, or the second tone we generate for a fixed end, one fixed end instrument, we have 2 minus 1 divided by 4. That becomes 4 here, minus 1, 3. So that's what we have there. Okay? So that's why we call it the third harmonic instead of the second harmonic, because we're not generating the second harmonic. It just goes into 3. 5, again, same idea. Another way you can sort of write this out is obviously just to remember it goes up by the odd number if it's one fixed end only or one open end. So that's another thing. So just remember, one overtone is the third harmonic if we're dealing with one fixed end of the instrument. Okay, that's just a really subtle thing that you need to make sure you differentiate clearly for yourself. Okay, so that's the main sort of difference we're looking into here. If it's two fixed ends, you can sort of see how it's fixed, it's attached to something. If it's open, it's not attached at all. First harmonic and 1, the next harmonic, second harmonic and 2, third harmonic there. If it's one fixed end and one open end, it's fundamental is the first harmonic, the next one is the third, fifth, seventh, ninth. Goes up in odd numbers. Keep that in mind. Okay, so we have the equations for standing waves. These are the equations derived for you. Okay, you could, if you would like, to try and derive the formula for frequency for these equations here. I might just show you how they relate. So we do know that the velocity of a wave is frequency times lambda. So if I substitute the formula of lambda being 2L over n, this is for our two fixed ends or two open ends, we get F times 2L over n. If I want to make frequency the subject of the equation, then obviously it's n times velocity divided by 2L equaling the frequency of the set, instrument. That could be for any string instrument, that could be for any flute-like instruments, things like that. Just remember, in terms of the SI units, length is in meters, frequency is in hertz, velocity is in meters per second. Let's try out this question here, and then you can try and do the other questions as well. So, we have two fixed ends at 22 centimeters long, and it has a vibrating fundamental frequency of 880. So, it says length of the fundamental frequency. Okay, it's vibrating at its so wavelength we're looking at. So the wavelength is equal to, let's just try and work out the values. Let's just go back to our formulas. We know what these all are. Okay, so that's the equation we use. F equals NV over 2L. Okay, so our fundamental frequency, n is equal to 1. Our velocity, we are looking at sound here, right? So velocity is about, let's just say 340, depending on what the question says. If it's not given to you, check the data sheet, use the number in the data sheet, and we know that the length of the string is 22 centimeters long. Now that 22 centimeters needs to be converted into meters, and that's the fundamental frequency we'll generate. The second harmonic, in this case here, is simply submitting or substituting the same value, but n is now 2. So that's how you do those questions. Okay, so you get that number there, 0.44 meters, 0.22 meters there. Now, slightly different, if we have a pipe closed at one end, so one fixed end, one open end, what is the length of the clarinet that we're dealing with if the fundamental frequency is 125 hertz? Now we know that the wavelength is 2n minus 1, okay, divided by L, okay? And we have velocity somewhere as well. I do believe velocity is up here. Quickly check. No velocity whatsoever. Okay, and this is 4L. Alright. Oops, just wrote that upside down. We'll change that. Okay, so substitute that in, we want to find the length. So we have 4L equals to lambda times that. We also know that 4 needs to be divided over 4. Okay? Now n is going to be 1 because that's our fundamental frequency. The speed is going to be 300, so that times 1 minus 1 divided by 4, and that will give us the length. That's going to be in meters because we put it all in the SI units. What's the wavelength of the next possible harmonic? So the harmonic we're dealing with is the third harmonic, or simply speaking it's n2, the second integer. So the wavelength here is whatever wavelength we had there. So from, just call it from answer A, divided over by 2 times n, which is 2 minus 1. And that will give us the wavelength as well. So that's what we get there. Okay? Those are the values there. Okay, some additional questions for you to try out. By all means, have a go at them. The answers are given to you here. If you want to know what the responses are, these are all shown to you here and here, like so. Okay, if you want to really test yourself out, by all means try and use these two equations and actually prove how you can get, the frequency, the wavelength, the lengths. How can you make them all come together using this formula there? I already showed you one. Try other ones if you want to as well. So let's kind of recap on what we've done today. We firstly talked about the concept of vibration. That's how we produce sound. We talked about the concept of harmonics, the most fundamental frequency, or the most basic frequency we have is called the first harmonic, or fundamental frequency as well. As you increase the pitch, that pitch goes up in a specific integer. So if we say the fundamental frequency of something is 2, okay, that's n1. Then the next pitch we generate is a frequency of 4. And then the next frequency we generate is a frequency of 6 hertz there. You can see the progression is a fixed progression. It's always going up by the same integer. That's what we mean by these harmonics. Each pitch is just a fraction or factor integer smaller than the previous pitch. Okay, so that's what we mean. Anyhow, hopefully that was helpful. Again, thank you for coming to the classroom. Always welcome you back to listen to more videos. Next one we're going to look at is for pipe instruments as well. See you next time.